going to present the supply chain design for modular construction projects, and it's your turn.
Okay. Good morning, everyone. My name is Leo, and I'm a PhD student from Imperial College London. And as you can see, my research topics is supply chain design for modular construction project. Today's presentation will starting with research context, research aim, and for result, a model has been developed to deal with foreseeable disruption and abrupt disruption on the construction site, and follow with conclusion. Okay, research context. A shift is occurring in the construction industry from stick-built to modular construction for pursuing better efficiency, higher project quantity, and less material waste. Okay. In the stick-built construction, raw materials are sent to the site directly, following the order by the contractor. But in modular construction, raw materials are sent to the factory in the first place and turned into modular components following rigorous manufacturing sequence. And these modular components are very large in size, so the factory and the site usually do not have enough storage space to store them, so they need to be put in a warehouse in between. Then they are dispatched to the site on a just-in-time basis. In this context, the definition for construction supply chain has altered, because now it has the characteristic of both manufacturing and construction. Thus, a new tailored logistic process needs to be developed. When developing this new tailored logistic process, some special features of modular construction needs to be considered. First, all the demand, the total demand and the assembly sequence for every modular components are known at a detailed design stage. And the second, just like I have mentioned, all these modular components are very large in size, so they need to be stored in the warehouse. This is especially true when the sites are in the urban settings. And those modular components are prone not to be put on the site because they are very likely to be damaged on the construction site in an open environment. The third one is that the assembly sequence is not so flexible as the stick build, so a delay in meeting a demand will postpone all the following demands. And the last one is that most of the modular components are tailor-made for a project, so in the end of this project, which inventory will reach zero. Unlike commercial product, there is no safety stock. The aim of this research is to develop a logistic model through mathematical programming to support decision-making in modular construction supply chain configuration. The supply chain configuration refers to the optimal production and inventory schemes. The model should be able to intake the data from the real world and output executable schemes which can help the contractor which doing modular constructions. And the total operational cost for the supply chain will serve as a performance index to evaluate the quality of decision making in this supply chain. As for result, a model has been developed to dealing with foreseeable disruption and abrupt disruptions. And this model has been tested on a case study of backroom parts, which are manufactured within the factory environment and transported through lorry assembly on site. Okay, for the foreseeable disruption, according to the previous studies, bad weather condition is a prevalently recognized deviation factor for construction schedule. So let's say, according to the weather forecast next week, the assembly rate is not going to be carried out as planned, and what operational questions could be asked by a logistics manager? First, what kind of assembly pattern will I run into next week, and what are the probability of happening? Second, how should the production scheme within the factory be adapted to minimize the total operational cost? Third, how many initial inventory I should prepare before starting next week, and how the inventory level should change? For answering these questions, a mathematical model has been developed through mixed integer linear programming. For the model input, also according to the previous study, the relationship between the daily assembly rate and the weather condition has been established through a semi-trapezoidal function. So this research has adopted this semi-trapezoidal function and integrated with the weather forecast data obtained from the UK Met Office to generate all the possible demand scenarios that may happen on the next week, and also their probability of happening. Then, that the model will first turn all the possible demand scenario into an expected scenario for representing the most likely situation that might happen in the next week, and based on which the model will output the optimal initial inventory quantity and the production scheme for each kind of part next week for minimizing the total operational cost. And it should be noted that those parts can be only made within discrete numbers, so the production scheme suggested will automatically be rounded to the nearest integer automatically by the modeling. And this is shown in the upper part of the slide. And in the middle part of the slide, let's consider an ideal scenario which is free from the negative influence of weather condition. The model can also propose its corresponding initial inventory quantity and the corresponding production scheme for minimizing the total cost. And by comparison the total operational cost, we can see that if there is a foreseeable disruption owing to the weather condition on the construction site, and if we take the suggested production scheme by our model, the rise of the total cost can be minimized to 1.87%. Okay, then for the abrupt disruptions, let's say the assembly process and the production sequence is running smoothly to meet the plan, but something unexpected just happened, then making the demand to drop become half of the original. And what operational question could be asked under these circumstances? First, how should the production scheme to be adapted immediately to deal with this unexpected situation? Second, how the inventory will change within this under these circumstances. Okay, and also for this case, another instance of a model has been developed and also based on a case study of bathroom parts and with different numbers. Okay, let's say the upper part of the slide shows the original planned assembly plan, and the model can propose the corresponding initial inventory and the production scheme. And let's say a strong wind happened on day 2 and there's no sign of stopping, making the demand become half of the original. Then, in this case, the model is able to stick to the production quantity on day 2 and propose the best production scheme on day 3 and beyond. This is for reflecting the fact that the undesirable situation happened abruptly, so the factory do not have a changeover time on day 2 to adopt a new production productivity on the day 2. So it will produce the production scheme on day 3 and beyond, and also show the change of inventory afterward. And by doing comparison in the total original cost, we can see if there's abrupt disruption and we take the suggestion by the model, the rise of the total cost can be minimized to 6%. Okay, for conclusion, the 3-tier logistics structure, which including the factory, warehouse, and site investigated in this research, is usually absent in the stick-built constructions. And the most favorable response in the factory and the warehouse for 2 kinds of disruption, which is foreseeable and abrupt, are being investigated in this research. And the model developed in this research is trying to serve as a decision-making tool for the logistics of modular construction. It also can to serve as a tool for realizing the lean concept in the modular construction. Okay, thank you very much for your time.